Hi everyone, welcome to meeting number 8 of the M2D2 series. We are very much excited to listen to this talk by Philippe Schwaller. Thank you, Philippe, for taking the time to present this talk to us today. A quick introduction for the speaker. Philippe has received his bachelor and master degree in material science and engineering from EPFL. While working for IBM Research, Philippe has completed a master field degree in physics at the University of Cambridge and a PhD in chemistry and molecular science with the Redmond Group at the University of Bern. In February 2022, very recently, this month, actually, last month, Philippe had joined EPFL as a tenure track assistant professor in the Institute of Chemical Science and Engineering. He leads the Laboratory of Artificial Chemical Intelligence, which works on AI-accelerated discovery and synthesis of molecules. Philippe is also a core PI at the NCCR Catalysis, a Swiss Center for Sustainable Chemistry Research, Education, and Innovation. Again, thank you so much for accepting our invitation and looking forward to your talk. To the audience, Philippe will be taking questions at different moments during the talk when he makes some pauses. So feel free to ask your question in the chat or raise your hand, and when the time is right, your question will be brought to him. Thank you so much again, and looking forward to it.
Thank you very much for this nice introduction. It's really an honor to be here today and present my work. I can really take questions during the talk, so feel free to write something in the chat and I'll try to monitor it. So yeah. Today I'll be presenting accelerating organic synthesis with chemical language models. And wait, I just have to, perfect. So I will start with a short introduction, then walk you through data representation and models, show you how those models were integrated in the RXN for Chemistry platform. Then we will explore chemical reaction space together. And in the end, I will try to show you what my models have learned and why they work. You probably all know that we have a nearly endless chemical space to explore. If we take drug-like molecules as an example, then the number is estimated to be 10 to the power of 60. This is a typical molecular design cycle where we ask the question first, what molecules do we want to make? And we can use generative models or property prediction models, and seen a lot of work also from Mila that in this direction. The end goal is like the experimental validation. We would really like to make those molecules in the lab and measure the properties. But this is not often done in all those machine learning papers because the make part is not that simple. And this was what I was focusing on in the last 3 years on this synthesis part, driving towards experimental validation. For machine learning, the data is super important. And for chemical reactions, we have pattern reactions. We could imagine to extract reactions from the literature, but it's typically not machine accessible, at least not in a way that we would like to have it. Then there are electronic lab notebooks that could be mined, or high throughput experimentation from which we could get some interesting reactions, but the space they cover is typically very narrow, and also simulations could augment the data we have. Next few minutes, I will be talking mostly about patent reactions because they are openly accessible, and I'm really thankful to Daniel Lau and also Roger Sale. Daniel Lau text mined the US patents and his PhD and extracted millions of chemical reactions. And one way to represent them are reaction smiles. Smiles are line notation from the 80s, and here you see the corresponding to the depiction of this string here. During my talk, I will mention atom mapping several times, and what I mean by atom mapping, because this is something that even chemists do not always know what it is that we have the information of what product atoms correspond to which reactant atoms, as you see here. But as Daniel, when publishing his data set, already warned us, well, typically correct atom maps are wrong in many cases and hence should not entirely be relied on. So yeah, this warning motivated me and my colleagues at IBM Research to try to develop atom mapping independent models. For the next 40 minutes, this will be the representation of choice, because it allows me to represent atoms as letters and molecules as words. And then after splitting those reaction smiles into tokens, we can borrow methods from human languages and apply them to chemistry. For example, we can map the reaction prediction task, where we try to predict the most likely product from a reaction, to a machine translation task. And I'm well aware that lots of this cool work comes from Mila, and we use the sequence-to-sequence models that were originally developed for human languages and for translation, for example, from Le Chinois to German Die Katze ist schwarz. And in reaction prediction, we also use this encoder-decoder architecture, but as an input, we have reactants and reagents. The encoder then computes the most interesting features, and the decoder predicts token by token, atom by atom, the most likely product until it predicts an end token, and we know that our product smiles is complete. I think you probably are all aware of that those early sequence-to-sequence models had the fixed size vector in the middle, and sometimes this was not enough information for the decoder to predict good outcomes. And that's why in natural language processing, the attention mechanism was developed, and this let the decoder focus on the most interesting features in the inputs. And no surprise here, the transformer architecture that was introduced at NeurIPS in 2017 by Wasrani et al. Is currently still our go-to architecture. And what were probably the two novelties that really made a difference is that they were fully based on stacks of attention layers, and also had this multi-head attention that let the decoder focus on the on multiple parts in the inputs. I think we worked directly after seeing this publication. We worked on the molecular transformer, where we used the transformer architecture to do reaction prediction, and the difference between sequence-to-sequence models with attention and the transformer architecture was huge. On common benchmark data sets for reaction prediction, we reached accuracies of over 90%, and back then we were much better than competing rule-based and graph-based approaches. Now, in the meantime, the graph-based approaches caught up, and it's more or less like the limit at 90% on those benchmark data sets. When I transitioned to the University of Bern, we asked the question, what is missing? And two things that were obvious to us were stereochemistry. Stereochemistry was one of the weaknesses of the molecular transformer and not handled at all by graph neural network-based approaches. And also experimental validation had never been done for those reaction prediction models, and at least not the new ones. And that's when I teamed up with Giorgio that you see here. He performed the 14-step synthesis of a lipid-linked oligosaccharide, and we used transfer learning approaches to learn to predict a very challenging reaction class, carbohydrates. Carbohydrate chemistry, as you see here, the carbohydrates have a lot of stereocenters, and it's really hard to predict this correctly. And on 3 different test sets, we could show huge accuracy increases using this transfer learning approach. This is just an example of a glycosylation reaction that we had extracted from a Jack's paper. And if you look here, the atom mapping is kind of obvious in this reaction. But even for a human expert, it would be almost impossible to predict whether it reacts in axial or equatorial position, and whether it would form an alpha or beta bond. And somehow, by learning from this carbohydrates reaction data, our model was able to predict this correctly. And those approaches we explored there can also be applied to other reaction spaces of interest. One thing that became popular recently are enzymatic reactions, because they're thought to be greener, and one question there is, how do we represent the enzymes? And I can show you 2 different approaches here. One from David Kreuter that just took the description as it was described by the human chemists, and tokenizes this, and combined basically this textual description with the smiles in the inputs to build this enzymatic transformer. And one alternative was explored by Daniel Probst at IBM Research, where he focused on EC numbers to represent the enzymes. I think future work will certainly go towards amino acid sequences as a representation, but those are the 2 works I know of. Now we will move from reaction prediction to retrosynthesis. And what do I mean by retrosynthesis? Got E.J. Corey the Nobel Prize in 1990, and what you want to do in retrosynthesis is you have a target molecule that you would like to synthesize, and you want to decompose it into known commercially available building blocks. And you do this by going backwards from the target molecule stepwise until you reach those commercially available building blocks. And we explored this in a collaboration with the University of Pisa, and there we had trained 2 different molecular transform models, one to do those retrosynthetic steps, like given a target molecule, predict the likely sets of precursors. And because it's impossible on a large scale to give all the possibilities to a chemist to evaluate them, what we use to score the different paths that we have had in our synthesis routes, we used the molecular transformer model, forward model, and gave it not only the reactants and reagents, but also the corresponding product, and let the model score the different suggestions to get a better evaluation of the different steps. What is special about the approach that we explored there is that we did not only predict reactants, but also reagents, catalysts, and solvents, as you see here. We tried to get as much information as possible and target more challenging retrosynthetic task. If you compare to what is typically done in literature, where only the reactants are predicted at this step. At IBM Research, one focus was on facilitating the adoption of those machine learning models by chemists, and to build the IBM Reaction for Chemistry platform, which is free. And I can show you a few screenshots. A chemist, even without having any coding knowledge, can just go there and draw molecules or paste the smiles as input, and then run predictions and get the outcome predicted by the model, together with a confidence score, and would also be possible to give feedback on the predicted reactions. Also, retrosynthesis is available as a feature. So for this compound here, the model would, for example, predict the bromo-Grignard reactions, which is totally reasonable. But yeah, let's have a look at some feedback that we got from Alessandro back in 2019.
Hello, my name is Alessandro Castrogiovanni from University of Basel, and today I want to show you how I use IBM Reaction for my everyday research. And I selected for you molecule to synthesize, and the program is giving me the retrosynthetic pathway, the most convenient retrosynthetic pathway. And for example, in the case of this ketone, the program is telling me how to prepare it with halogen metal exchange, and then addition of the lithiated species to the acyl chloride, and then the protection of the ether with pyridinium chloride to deliver the product. But this is not just the only result. There are other outputs given by the program, and I will show you another one. In this case, they do the halogen metal exchange on another substrate, and then they perform the oxidation with manganese dioxide and deprotect. And in my opinion, everything makes sense, and is helping me and my colleagues to achieve the substrates, the synthesis of every substrate.
Such feedback motivated us to continuously improve our models. And you might wonder what's next, at least for IBM Research. And let me just on one slide point you to RoboRXN. Imagine you're a chemist at home and you do this creative process of designing a molecule. Then you connect to the cloud, where you get access to a synthesis planning tool. But not only that, you can automatically convert all the different steps in your synthesis into recipes, into steps, actions that you could then perform in the lab. Or if you have access to a cloud-connected synthesis platform, you could also directly execute them on the platform. And IBM Research in Zurich has a prototype of such a synthesis platform. And at this point, let me just point to Theodor Leiner, my former supervisor at IBM Research, and the RoboRXN team that worked really hard on the whole integration of those different approaches. Here we have this RoboRXN platform in action for the synthesis of a photoacid generator. This was predicted by the retrosynthesis tool that I had described to you. One crucial part behind this platform is really also the machine learning model that translate arbitrary chemical reactions into the sequences of actions, including reaction conditions, and also the order in which we have to add the different components into the reactor to then run the reaction. And this was work done mainly by Alain Vaucher.
Philippe,
yeah.
There is a few questions in the chat, and I feel like this might be a good moment.
Okay, yeah, this is really, I can really here stop in 30 seconds because this was the first part on sequence-to-sequence reaction models that we've seen for reaction prediction and synthesis planning. And yeah, let's take some questions on this first part before I move on. So do you want to?
Yeah, I can read out some of the questions. So there was when planning reaction route, should the model take into account the reaction condition, temperature, pressure, light? So basically, I guess, does your model take into account all of that in predicting the reaction?
So yeah, okay. The early models that we had only took into account reagents, solvents. So part of the reaction conditions were also catalysts, but not only the structural information, but not like temperature, pressure, light. There was some recent implementation into the platform where there was also the integration of temperature and light, if I'm not mistaken. So models are being built that include conditions, but I think they still need to be explored better, and it's really hard to predict those conditions because the data is a bit sparse, and then it's also that if you have one reported reaction temperature, then it might work for a large range of temperature, but most likely the chemist has just copied something that he or she got from the literature and tried it out. It led to the expected product, and it was not really optimized. And yeah, no, but it's definitely an interesting topic to look
Okay.
on.
One question from Emmanuel: do you perform any online learning using the chemist feedback to update the models?
So we don't. So far we didn't. There was a long time this feedback options, but we didn't have access to the actual data without the user giving us the feedback. And but also there, it's not always obvious for which reasons the feedback was given, and sometimes we don't have a corrected product or something like that. So we worked with a group of experts when I was at IBM Research, and we tried to get their more offline feedback to improve our models and to focus on specific reactions that were not well predicted back then. Yeah.
Okay, one last question. In IBM retrosynthesis, most predicted trees contain only one layer. Is there an option to increase the number of layers in the tree automatically?
So what do you mean by one layer?
I can ask Gemi to come off mute and ask the question herself.
Yeah, maybe it would be helpful to.
Hi, Philippe.
Hi.
So my question was, when the synthesis reaction tree is predicted, it only contains like one set of reagents and reactants. But sometimes one of those reactants might not be commercially available. So in that case, we can like go back another tree depth to enhance like the tree depth basically.
Yes. So
most of the time I do it manually, but is there a way to like get it automatically in case that the
okay. I know that it definitely works in the interactive mode where you do it manually. I'm not 100% sure how well it's integrated in the API for the moment. I think if you maybe open a GitHub issue on the API, people will be able to help you. But no, it really makes sense to extend it and make it also.
Thank you.
Yeah.
That's all for the question.
Thanks a lot for the questions. Is it? Yeah. Okay. I will continue. So this was basically my first part, focusing on the sequence-to-sequence transformers. And in the second part, we'll move to encoder-only transformers that get as an input a complete reaction smiles and then predict a single value or label. And we use this for reaction classification and yields prediction. So let us zoom into such a transformer model. You probably all know that, but the transformer model is made of stacks of self-attention layers, the encoder. And what it gets as an input, in our case, are those tokenized reaction smiles. Then we have every self-attention layers has different heads that all can learn different functionalities to attend the input tokens and learn better and better contextual representations. Why is context important? Yeah, if you think of the word bank, for example, then it has a completely different meaning depending on whether you speak about the river bank or the bank you get money from. And similarly, in chemistry, you have all those atomic tokens. They're often the same, and a nitrogen atom, for example, might have a completely different meaning depending on its nearest neighbors, the atoms in the molecule, or in the complete chemical reaction. Once we have this encoder trained, we can add a regression or classification head and tackle a downstream application. The training typically happens in 2 stages. The first stage that we often use is masked language modeling that you all know. We hide or mask different input tokens and let the model predict the masked tokens. And like that, we can generate quasi-unlimited training data, and I would argue that the model has to capture some chemistry, chemical knowledge to be able to perform well on this task. Because you cannot replace any atom with any other atom. And yeah, and then we tackled, for example, reaction classification, where we try to predict the reaction class that corresponds to a specific reaction smiles. And on data from NextMove software, we could show that we're more than 98% accurate on the test set. So the models were able to learn the rules that generated this ground truth data. But what for me in this project was more exciting is that we took away the last layer and looked at what the encoder produced as vectors for the different reactions. We had something like a data-driven reaction fingerprint, and we could use this to cluster chemical reaction space and generate those chemical reaction atlases. Then the representation, this tree-like representation, is based on the TMAP algorithm by Daniel Probst. Here you have such a reaction atlas in action. You can display different layers, categorical properties of your reactions, continuous properties. You get an immediate feeling of like the local but also global features of your data set. You can zoom in, display the reactions and additional information that you have. And this allows you to quickly compare nearest neighbors. We can use this reaction fingerprint also to query for similar reactions when we do prediction. For example, here in this Diaz-Alder reaction, predicted by the model, it's a bit slow, but yeah, the result would come very soon. And here's the expected product. And now we can use the fingerprint to query the most similar reactions in the training data set, for example. And those are all Diaz-Alder reactions. And for those reactions, because they were done at some point and described in the patents, we have additional information and we can have a look and check the procedures. And this gives really the chemist additional information that a good starting point if he or she wants to run the reaction, the predicted reaction, somewhere in the lab. There's open source code available for that, and this reaction fingerprint code was also tested by some folks at AstraZeneca, and they wrote a reusability report in Nature Machine Intelligence. Another downstream application that we tackled is the prediction of reaction yields. And we first, okay, yeah. Sorry, it's much better if you,
There's
Happy
a question
to
from Professor Benjio. I don't know if he's still there.
Yes. Hey, Philippe, this is great work. My question is about the atlas.
Yeah.
So why should it be a tree? Because you can get to more or less the same thing from different paths, kind of, right?
Yeah, definitely. Yeah, I think also if I go back to the atlas, I have to quit the, maybe like that. Can you you see it?
Yes,
okay.
yes.
Yeah, no, it's. I think it has to be those paths are somewhere clearly broken, and probably like reactions that are here could also be connected to somewhere else. But around the border of the atlas, I didn't work myself on this. Dimensionality reduction algorithm. This is really work that was done by Daniel Probst during his PhD.
Okay.
Yeah.
So I mean, I guess the tree is just because it's convenient for the algorithm that organizes everything in this structure.
Yes. Yeah. It's but then it's. We found some super nice, in the different branches. There were really like reactions that had 2 different or 3 different classes, and they were still clustered in the same branches. And it's kind of impressive to see how those, they were put together.
Okay, thanks.
Yeah. Another question, I guess, from Janet.
That's a question.
Hi, yeah, I have a question. I just want to know, how do you measure the distance between the data points? It is like a cosine distance in the reduced dimension space, or?
Yeah, I think there are different distances that were implemented in the TMAP algorithm. I'm really not super familiar with the exact details, and but I'm more than happy to point you to the code and everything, to the tutorials, and also those nodes that are close together are typically taken together and from one point on this this tree, and in the end I think here we had roughly 50,000 reactions.
Thank you.
Yes, back to reaction yields and more trees. So this one thing we tried is to look at the USPTO data, so the patent data, and we extracted the yields for different weight scales, and we tried to predict them with our models, but long story short, it didn't work at all. I think in the patent data, there's just too much inconsistencies. The yields were measured by different people, different machines, with a different aim in mind. Some of them wanted to optimize the reactions, others wanted just to show that the product was somewhere in the desired product was somewhere produced during the reaction, and this was really hard to learn. what we then tried is high throughput experimentation reactions, and we focused on a data set that was published by Abigail Doyle, and that was describing Buchwald-Hardwick reactions. And there, what is convenient is that all the reactions were run in the same conditions, and the yields were measured by the same equipment. And the Doyle group in the original publication, they used DFT descriptors and tried out different models, and concluded that their random forest models were working the best. And 1 year later, there was the Glorious group that tried to just concatenate different structural fingerprints and predicted also on this reaction data set. And we tried to learn to predict yields using those reaction transformers, and hoped that the transformer model would learn the fine-grained differences between the different reactions just by, and their impact on the yields just by seeing a lot of them. And here were the results that with one-hot encoding, the DFT descriptors, the multiple fingerprint features, and the results that we then got with the transformer model. When you think of deep learning, usually you think that you need a lot of data, and that's why we tried also to predict with smaller and smaller training data sets. And we're happy to see that using some data augmentation techniques, we could match the DFT descriptors even with less than 100 training data points. One question is, why do those transformers work so well in chemistry? And that's when I teamed up with Ben Huber and Hendrik Storwald, the amazing visualization experts from, you might know them maybe from Expert, for example. And we took the USPTO data, so millions of chemical reactions, used this supervised training task, so just mask language modeling for chemical reactions. And then we inspected visually what our models had learned. And yeah, here it's just important for you to see that the model had 8 heads and 12 layers, and it was an Albert model. And if we then use chemical reactions as an input, we can start inspecting different layers and heads in the model and see the patterns, the attention patterns that resolves. And here, to understand this, you have the precursors and the products on the top, and the same precursors and products on the bottom, and you have the attention weights that are displayed in between. And for this atom here, it would focus mostly on the nearest neighbor in the molecule. And we were like going layer by layer, head by head, and trying to figure out what those models had captured. And at some point, we saw this pattern here appearing. And if you look closely, the precursor atoms mostly point towards product atoms, and the product atoms towards precursor atoms. And if you remember the beginning of my talk, this really resembles atom mapping. So how atoms rearrange during chemical reactions. And using this discovery, we built RXNMapper. What RXNMapper can give you is, if you have a reaction smice without atom mapping, pass it through RXNMapper and you get back the smice with atom mapping. And on an independent benchmark, where they curated 1,800 reactions and tested even commercially available tools. RXNMapper, which is open source, was ranked best and much better than the alternative that we currently have in open source, and that was used to map the original USPTO data. So maybe, yeah, has RXNMapper learned some chemistry? And this here is an example we got at some point from a user that was telling us, look at that. It doesn't even map the benzene ring here, this ring here, to the benzene ring on the other side. What is happening? And we were puzzled a bit ourselves, and we looked at the attention patterns. And if you see here, you have mostly just straight lines, and either straight lines or it's going to this class token. And but it's an unrealistic reaction. There's something missing. So we added the reactant that was missing. And as soon as we added that, we got back those nice atom mapping patterns. So to some extent, it has learned a bit of chemistry, and it's not just done as a rule-based model and would always map a benzene ring to a benzene ring. It's also really fast. GPU accelerated, we map at roughly 7 milliseconds per reaction. And once we have a huge reaction data set mapped, we can extract different information like the reaction center, bond changes, basically the grammar of chemical reactions. And this can then be used to improve downstream applications. On the next slide, I will just show you where atom mapping is used in synthesis planning. You might be aware of the work by Marvin Segler that published his template-based multi-step synthesis planning algorithm in Nature a few years ago, or the work by Connor Colley. You have also amazing work on graph neural network-based approaches that predict bond changes and graph edits. And in the first part of my presentation, I was showing to use smiles-to-smiles approaches. So the two upper approaches are atom mapping dependent because they require it to generate the training data. You need the atom maps to extract the templates or the graph edits. On the other hand, we always focused on atom mapping independent models, but we lose some kind of information because we don't have this correspondence, and it would be nice to have it for interpretability. So I'd say in the end, all those approaches benefit from having better atom maps. If you want to use RXNMapper, there's open source code available. We have also a demo online, so you can just paste in your reaction smiles and give it a try. Actually also use it sometimes when I want to extract the reaction template, and just go online, paste my smile, get the atom mapping, and then extract the template from the reaction. And yeah, you probably all know this graph here, and language models are getting bigger and bigger. But in my case, the molecular transform had 20 million weights, the reaction fingerprint 6.6, and RXNMapper we went down to 800K. And all of the models were trained on one GPU in less than 2 days. So it's kind of feasible for everyone. And as a summary, in the first part, you've seen a reaction transformer, sequence-to-sequence models for reaction prediction and synthesis planning, and in the second part, encoder-only models for classification and fingerprints, reaction yield predictions, and atom mapping. I hope I've been able to convince you that we can get something out of like applying language methods to chemistry. If you're interested, there's this Reaction for Chemistry platform that is free, and there's tons of tools there, not only for synthesis planning and reaction prediction. There's also a simulator of this RoboRXN and paragraph to actions and all that stuff. We have developed this data-driven reaction fingerprint, and there are tutorials online to create your own reaction atlases or T-maps in general that you can apply to nearly anything. And I guess like what my personal highlight of the work I've done during this time at IBM Research and the University of Bern was clearly to like inspect the models and see that they learned some specific chemistry related patterns that we could then use to build this RXNMapper tool that is actually useful. Yeah, I think for the future, there's still a lot of stuff to solve, and it will be a combination of different data sources and new models, and maybe so, yeah, closed loop approaches, and putting back some also human knowledge into those models. And yeah, I'm super excited to be starting my work at EPFL, building up a group, and with this, I would like to thank all my amazing collaborators during the last few years that made this work possible. And let me just highlight Theodore Leiner, my former supervisor at IBM Research, and Jean-Louis Raymond, my PhD advisor. And thank you very much for your attention. I'm more than happy to answer all your questions.
Thank you so much, Philippe, for the great talk. We very much enjoyed. There's a lot of question in the chat. I will just call people name and they are happy to, they can come off mute and ask the question themselves. Professor Joshua have some question about yeah, where the code is available, and don't know if you want to clarify that.
Well, it seems that it's been answered, right? So I think we're good.
Okay, cool. Emmanuel also, no, not Emmanuel, Harry has some question.
Hi, yes, my name is Harry. I was wondering, in fact, there are two questions. The first question is that it seems the SMICE representation work quite well in this case. And nowadays, I see a trend that people leverage graph representation for that. What's your opinion on that? The second question would be like, as Professor Benjo pointed out that the embedding space seems very sparse and tree-like structure. I wonder if you have any observation on why it happened in this way. It's very sparse to me, the embedding space. Thank you.
Okay, the first question is a very good one. Yeah, you have I think SMICE were really useful in the past because those language models were a bit ahead of the graph-based models, I would say. And the second thing is that stereochemistry is really hard to encode in those graph-based representation, because their stereochemistry is not only dependent on the nearest neighbor. And in SMICE, we can just describe it in a special token. And it was already there, so there was no adaptation needed to the representation to make the models work. And while there are some benchmarks without stereochemistry, if you want to make anything credible, I would say for chemists, you need to incorporate stereochemistry.
I don't understand this. Sorry, because any string that corresponds to a data structure like SMILES,
yeah,
can be mapped to a graph. So why is it you can't do the same thing with a graph?
Okay, so stereochemistry, if you have a stereocenter, then,
I don't know what that is. I'm sorry.
Okay, yeah, no, okay, so it's like stereochemistry is describing 3D information. It's like, it's describing whether it's your left or your right hand, basically, of a molecule, and they're not superimposable.
Okay.
And it's basically, it's to capture this information that whether it's the left-handed molecule or right-handed molecule, and to capture this just by having nodes and edges in a graph. In SMICE, it's incorporated in how the different branches are ordered. So it will tell you in, yeah, yes, and that's why it's in a way easier incorporated in those strings than
Okay, but you shouldn't think of a graph necessarily as you have one node per atom. You can encode any information in the nodes and the edges.
Yeah. Yes, no, that's. I'm sure that there's a lot of development that is happening, and that there are possibilities to encode it. Yeah, I think there was also work by Connor Colley at some point that was trying to incorporate specifically this information into graphs. And but for I think it was just easier to work with those models those last few years, and without having to care too much about how to incorporate it into the model and into the representation that we used as an input. Yeah.
Thanks.
And yeah, there was the second question about the sparsity in the embedding space. Can you just repeat where do you mean exactly with the sparsity?
So thank you for the answer to the first question. My second question is that if you look at the RXN space, embedding space in your model, it seems it's quite sparse in a tree structure. I don't know why it happened in this way, or do you have any observations on why it is so sparse? And
I think it's okay. This has to do with how TMap does this low dimension. Yeah, it reduces the dimensionality of your data, and I think it pushes away different branches and targets really this creation of a tree-like structure, and it fills this whole tree. It would be interesting to see how, I don't know, what would happen if we put it into a t-SNE or another, or just do a PCA on those embeddings, and if it would, I think it would end up with lots of small islands corresponding to the different reaction classes.
So did you encode any prior into your embedding space, or does it's happening this way?
We didn't encode any prior into this space, no. And even we have in our publication, we also have like one of those trees describing, showing the space after pre-training, before it was fine-tuned on reaction classification. And even there's already some structure inside.
Okay, thank you very much.
Emmanuel has a question about RXNMapper.
Yeah, thanks, Philippe, for your talk. I actually had two questions. The first one was about the RXNMapper. So maybe can you comment on the accuracy of that compared to doing something like a substructure matching, which is what the RDKiral's tools from the command group is doing?
Yeah, I think it's a very good question. I think I think the beauty of this approach is that it has never seen atom mapping, and that I think there were lots of comparisons with different. Yeah, okay. Here I have a comparison on like a small test set that was published by in NatureCom that was called Map It, where there was a lot of also expert knowledge included. Let me see if I have a better comparison than that. Yes. The thing is, most of the approaches are closed source, and you cannot really compare to them. To which approach are you really referring to? Because
I was talking about the one implemented in RDKiral, but practically anything that is using substructure matching.
Okay, Yeah, okay. I think archiral is okay. Don't you have to start with an atom mapped reaction when you are using archiral? I don't know. This I might not be aware of, like the atom mapping. I guess that it's like typically what is done is that you have rules that are matched, and if you have a reaction that matches a rule, then you get the atom mapping as a side product. But then you have to encode every single rule that every single reaction rule into your atom mapping generator. This is something that is, for example, done by NextMove software to produce the reaction classes, and they get as a side product atom mapping out of it. I think really the beauty of this approach here is that the model was trained on reactions without atom mapping and captured this atom rearrangement signal in some kind of way, and we could use it to build reaction mapper. It's yeah, but it would be nice to have. I think the only benchmark that really exists that we tested also a few of the closed source approaches. It was this one here, and I think I would go there and have a look at the results there. And but I don't think they included archiral, and I'm not aware of the atom mapping functionality. Yeah. Sorry.
Thank you. My other question was about where the field is heading. So recently there have been a lot of large language models for chemistry that have been pre-trained on molecular data. And some of them have been tested on chemical reaction forward and retrosynthesis prediction. But I feel like we are getting better models, obviously, but on the question of data itself, it's not comparable at all to NLP. So, like, can you maybe comment on where do you think with the fields of like language model for chemistry is heading, and maybe what we will need to like to improve it further?
Yes, that's a really nice question, and I think I would not only look at language models for chemistry. I would just look at machine learning in this chemical synthesis space in general. I think what will become more and more important is to like capture the properties of catalysts that can change like the reaction outcome in like a kind of unexpected way, and to work with really small data sets and do some kind of few shot predictions that could become more and more useful for experimental chemists. I have the feeling that in a lot of the tasks that we currently address in machine learning, the benchmark more or less at the maximum. For example, in reaction prediction, we should have more, maybe more specific new tasks to tackle, and that are also more realistic in the end, and where the models that perform well on those are easier transferable to what the chemist needs in the lab. I'm also not a huge fan of, for example, this typical single-step retrosynthesis benchmark with those 50,000 reactions. And in retrosynthesis, you have many different possibilities to to synthesize a molecule, and the one you reported might not be the best one. And it's been shown in a few publications that models that actually predict that have a high accuracies on those single steps, as soon as you put them into a multi-step planning system, then they actually perform worse than other models that can predict more diverse reactions, because there's some kind of bias in those single steps that is actually not useful for real world problems, I'd say. Yeah, so I think new benchmark would be really important, and if that describe challenges that are closer to reality and to what experimental chemists can actually use.
Thank you, Philippe, for the answer. There's a lot of questions remaining in the chat, but I fear those will be unanswered for now, and maybe you can tackle those on Twitter or whatever, by whatever channel
you save the chat, maybe?
Yeah, we will save the chat.
It would be nice if you can export the chat, and
okay. So we'll be exporting the chat, and some of those questions will be answered when we share the recording on Twitter by Philippe, as he wants. So again, thank you so much for the talk. And thanks you all for attending this one, and looking forward to see you again next week.
Thank you very much. It was a great pleasure to be here. Thanks a lot for the great questions, and